Remember the Transformers movies from a while back? Well, I'm here to tell you that Transformers could become reality with origami. Origami is super useful in robotics because of its unique properties. Today, we're going to talk about a principle called the Poisson effect. This concept can help tell us why origami is so special. To demonstrate it, let's use some tessellations. First, we have this one, which is a variation of the water bomb pattern. I'm going to pull this tessellation in the longitudinal direction, like this. What do we see? We see the tessellation's length increasing in the longitudinal direction, which means that the material has a positive longitudinal strain. Well, what about the other direction? How's the tessellation changing in the lateral direction? As I'm pulling the tessellation longitudinally, it is getting smaller in the lateral direction. In other words, its distance along the lateral direction is shrinking. This is due to its negative lateral strain. This phenomenon is called the Poisson effect, which explains that a material when stretched along one axis is compressed along the perpendicular axis, like this. Now to measure the Poisson effect, we use the Poisson's ratio. It tells you how much a material can change laterally based upon how much you stretched it longitudinally. The Poisson's ratio in equation form is the negative ratio between the lateral and longitudinal strain. We can see here that there is a negative sign next to the lateral strain symbol. This is because in most materials, they stretch and compress in opposite directions, as in their different directional strains have opposite signs. Thus, by adding a negative sign to the ratio equation, most materials now have a positive Poisson's ratio. But are there any materials with a negative Poisson's ratio? There is indeed. Negative Poisson's ratios are rare, but of course they exist. Researchers have found it in origami. Now let's take a look at another tessellation called the Mura-Ori pattern. What happens when we pull on the sides of it, expanding it longitudinally? Instead of it shrinking laterally, we actually see this expand along the lateral direction as well. And let's try squishing it along the longitudinal axis. It squishes laterally too. This defies the Poisson effect since it expands in both directions at the same time and also compresses in both directions at the same time. Because the Miura pattern has longitudinal and lateral strains in the same direction, it has a negative Poisson's ratio. With cool patterns like these, we can develop awesome flexible deployable structures. That's the beauty of origami. We can design and manipulate patterns to create special mechanical properties like this negative Poisson's ratio, which we couldn't have created with normal unfolded materials. Origami has been used in lots of innovative devices, such as satellites and medical stents. Maybe one day we can make transformers using origami parts. Now that's something I'd like to see.